Now we're going to look at a disk of charge, which effectively means a big flat circle. Now, because of that, we actually have to start thinking about surface charge density. And in that case, surface charge density eta is going to be the total charge divided by the area, pi r squared. How you can approach this problem in the laziest way, that's still honorable, is to actually think about this as a sum of rings. So don't always just say that you need to break it into a little delta Q. Don't just try to make a point charge here. You can do that. It's not wrong, but it's going to be a lot more work. And inherently, we already know what the electric field from a ring is. That's what the last video was on. So this is what our electric field from a ring is, but now that is the individual electric field in the z direction from one ring at our point. And we simply say, oh, well, I'm going to take lots of different rings that each have a different radius and then calculate their electric field. So not only do you have to consider that they have a different radius, but you also need to consider the fact that they have a different charge. And the reason for that is that your charge density is the same over the entire surface. But if we think about taking our ring and unrolling it effectively, we have some delta r, which is the thickness, which later is going to factor into our integral. But then we have a length, 2 pi r, that depends on the radius of the ring. So this is a case where you definitely want to use your surface charge density because each ring is actually going to have a different area. So you need to multiply our delta area by our surface charge density to get what our delta Q is. The answer here, after you actually do all of that algebra and do the integration, looks like this. Note that we have eta now, we don't have Q, though you could actually just rearrange it and plug this back in for eta. Note that our 4 pi epsilon naught, because we have a pi floating around from it being a circle, has just actually become 2 epsilon naught. That's not a typo. And then there's an interesting term on the inside, which is a 1 minus term. And now we have z, which is the distance you are from the center. Again, this is only true. This equation is only valid if we're working on the axis of the disk. And then we have z on top over square root of z squared plus r squared. So again, to go from here to there, these two lines are separated by maybe a page or two, depending on how big you write, of algebra, geometry, and calculus. However, the shortcut, if you will, is to notice that we can do this as a sum of rings, though this will actually be an integral sum, not just an addition, rather than actually looking at point charges. Now let's think about some limiting cases, because again, that's always a good way to get a feeling for what this is going to look like. So the first one is to think about it being very far away. Again, for a ring of charge, we saw that it did simplify down to being the electric field from a point charge, so we should expect to say the same thing here. If I'm really, really far away from a circle, it just looks like a dot. So that means that z, the distance from the disk itself, is much, much greater than r, the radius of the ring. Now, to actually do this out properly, you need to use the binomial approximation, because otherwise, if you just say, well, let me take r, make that go away, I'm left with square root of z squared over z is 1, 1 minus 1 is 0. Hey, my electric field is 0. That's not very helpful. So we can't do that. The binomial approximation is something that we did cover last semester and is on the equation sheet. To remind you, the idea of the binomial approximation is if you have 1 plus x, where x is very small compared to 1, raised to the power n, where n could be fractional or negative, that is then approximately equal to 1 plus n, so same n, keep it negative if it was before, multiplied by x, where it's that value. So to actually work with this in the binomial approximation, you do need to actually pull out a z squared, so that you would have 1 plus r squared over z squared. Then you can use this to simplify it down, do some math, and you actually get something a little bit different. So the approximation leads this inside term, and one trick, so this and that are exactly equal, and then we're only doing the approximation from here to there. Whenever you have something that's 1 minus something kind of small, something close to 0, use the binomial approximation for this because your first term is always going to be 1. So that's one hint here. But then we do the approximation. Again, I'm not going to show you all of the steps, but note that we are left something with z squared on the bottom. That's good because that is how we expect the electric field from a point charge to fall off. But I don't quite see my 4 pi epsilon naught, or my q, right? But remember that this actually was q divided by my area. My r squared relates to my area. So in fact, if you just change out what this variable is and do some rearranging, you get exactly back the electric field from a point charge when you're really far away. And that's again what we expect. Now, the other question you could ask is, what if we make r go to infinity? What if we're very close to the center of the disk? And again, this is a case where we can do that, but we don't know what we expect. So we're going to do that in the next video, which is going to be looking at the field from an infinite plane, which would be the opposite limiting case.